Freshwater aquatic communities can be classified into two groups. One being the lotic communities that include rivers and streams of flowing water bodies, and then two, the lentic communities, those water bodies that are relatively still, like lakes and ponds. The concept of stream order is used to classify lotic or flowing water bodies. Stream orders range from 1st to 12th, with first order streams being the smallest headwater streams, and 12th being the largest rivers. Stream order is determined by first looking at the headwater streams. So the headwater stream starts with the number 1, that is a first order stream. You're only going to go up to the next order when you have two of the same orders come together. So we have a stream order 1 and a stream order 1 come together, we make a 2. So now we have a second order stream flowing, and now it intersects with another second order stream. Then we're going to bump up to the next level stream, the third order stream. But notice here I have a third order stream here, and I have a first order stream flowing into it. I do not bump up to a fourth order stream. In fact, as I continue down here, it's still a third order stream, still a third order stream, and I have a second order stream flow into it. This water body remains a third order stream, and I get another first order stream flowing into it, stays a third order stream. It is not down here until another third order stream flows into this water that it bumps up to be considered a fourth order stream. So it's a little bit funny math, but you just kind of have to remember that it's only going to go up to the next level or order stream when it has a river flow into it that is the same order. First to third order streams are considered headwater streams. Fourth to sixth orders are considered medium streams, and finally 7th to 12th order is considered a river. The value of this classification scheme is that we can infer physical, chemical, and biological properties of these streams based on just knowing what order stream it is. So let's look at these properties and compare a first order stream to, say, an 8th or 9th order stream. And we'll look at the differences between temperature, dissolved oxygen levels, the source of nutrients for that stream, nutrient spiraling rates, the benthic structure, and the living organisms that are at the base of the food chain in a first order versus like an 8th order stream. So let's think first about temperature. How would you think temperature would differ between a first order stream and an 8th order stream? Lower order streams are typically colder than higher order streams. This is because headwater streams generally lie at higher points in the landscape. Higher elevation equals colder air temperatures, which also equals colder water temperatures. Headwater streams also are typically more narrow and therefore more shaded. You increase the amount of shade over that water body, you are decreasing the amount of light that can reach that water, and therefore, of course, the water temperature as well. Note, however, that large rivers tend to act a lot more like lakes, and you will have a little bit more of a vertical gradient of temperature. So the surface water will be very warm, but those waters underneath will be cold. Overall, still, the water in a larger order system is going to be warmer than the first order, second order, third order streams. Now let's examine the difference in dissolved oxygen levels between a first water and 8th order stream. In order to explain why different stream orders might have different concentrations of oxygen in them, we have to remind ourselves of some of the chemical and physical properties of water. So remember that water is a polar molecule. It has a plus and a negative charge. Oxygen is not. Oxygen gas is 2 oxygen atoms double bonded to each other, and it does not have a charge. So therefore, water and oxygen are not chemically attracted to each other. Oxygen gas does not have a charge, and therefore it doesn't dissolve in water. Therefore, oxygen levels in water are relatively low. This is the stress for organisms living in water, and many have adaptations that reflect their long-term evolution under this selective pressure, such as this predaceous diving beetle, that is able to hold onto a water bubble under its abdomen and access the oxygen in this bubble while submerged. So if oxygen is not dissolving into water, how's it getting in there? Well, by the process of diffusion. Diffusion is the tendency of molecules to move from a region of high concentration to lower concentration. Now, as you can see illustrated in this diagram, there's typically a higher concentration of oxygen in the atmosphere than in the water. So the oxygen levels in water bodies are low compared to the atmosphere. That's going to cause the molecules to diffuse into the water body, move from the area of high concentration to low concentration. This measurement of the concentration of free, not chemically combined oxygen gas in water is called dissolved oxygen. Factors that affect dissolved oxygen concentrations in water include temperature. So as water gets colder, the kinetic energy of both the water and the oxygen molecules decrease. So they are moving slower. And that allows the hydrogen bonds between water molecules to strengthen. And that makes it harder for the oxygen gas to escape. So you can see in the diagram here that as temperature increases, the concentration of oxygen gas in water decreases. This is a negative correlation. Another important factor is the surface exchange with the atmosphere. So the more contact there is between the water and the air, the greater concentration of oxygen in that water body. So the more turbulent the water is, if it's flowing over rocks, when the water body turns over, you're going to increase the amount of oxygen throughout that column as well. Other factors that influence it include the amount of photosynthesis, which is going to add oxygen to that water body, decomposition and cellular respiration, which consume oxygen out of that water body, and also some types of pollution will also decrease the amount of oxygen levels in water bodies. The oxygen concentration of headwater streams is therefore typically greater than in the higher order streams. This is for two reasons. One, oxygen content of cold water is greater. We've already established that headwater streams are colder, therefore they hold on to more oxygen. Second, headwater streams also tend to be more turbulent. The oxygen concentration of flowing water is higher because of the greater contact of water with the atmosphere. So headwater streams are shallower, they're rockier. That's going to increase the air to water interface and increase dissolved oxygen levels. What is the difference in the source of organic-based energy in a headwater stream versus a large river? Now, the ultimate source of energy is, of course, the sun. But what organism is fixing this energy into an organic molecule and thereby making it available to the rest of the food chain in these two different extremes of lotic communities? In a headwater stream, the source of that organic-based energy is external. It is coming from terrestrial detritus. The trees that are shading that headwater stream are the ones that are able to fix that energy from the sun. And when those leaves fall into the stream, that is the source of organic-based energy that a variety of different critters are shredding up and making available to the rest of the food chain. In a large river system, the source of organic-based energy is internal. It's coming from the life that lives in that water body itself, starting with the phytoplankton that's able to capture the energy from the sun and turn it into an organic-based molecule. That is what's setting off the food chain, either through the direct consumption of those organisms or even through the decomposition of dead aquatic life. The two terms that we need to be familiar with here is allocathonous, which refers to an external source of energy, which is more common in the headwater streams, and then autocathonous, meaning internal, creating, self-created. The differences in nutrient spiraling rates between these two systems is fairly straightforward. The lower order streams will have a faster nutrient cycling rate, and the higher order, larger river complexes, the rate at which nutrients are being cycled through is much slower. This largely has to do with the depth of the water column and the movement of the water through that system. So the headwater streams are very shallow. As things die and fall down to the bottom of the stream, they are constantly being mixed and meeting oxygen-rich waters where they can decompose and release those nutrients, as opposed to the large river complexes, where when things die, they're falling down to the bottom. Oxygen levels are low at the bottom of that water body. Decomposition is not happening at a fast rate, so it takes a much longer time for nutrients to be re-released into the system and available to other organisms. Differences in the benthic structure of a headwater stream and large river complex are also fairly straightforward. Headwater streams tend to have more coarse sediments like large rocks, pebbles, and gravel, as opposed to a river system that is going to have much finer sediments like silt and clay lining those riverbeds. The living organisms at the base of the food chain will also differ significantly between a headwater system and a river complex. Because the source of organic-based energy in a headwater stream is coming from external sources, the terrestrial detritus, what's kind of kicking off the food chain in that water body is a diverse assemblage of aquatic macroinvertebrates that are shredders, or grazers, or predators, collectors, and there's also some microbes. In a river complex, what's kicking off the food chain here is phytoplankton. So in summary, we have this river continuum concept that starts from the first order streams down to the 12th, where we have this known transitions in the biological, physical, and chemical properties of these lotic communities.